Another important region is the temporoparietal occipital junction, which subserves naming and consists of parts of the middle and posterior parts of the superior temporal gyrus, the middle temporal gyrus, and the inferior parietal lobule. That is the angular gyrus, and the fibers that is involved is the SLF3. Okay, so now let's look at the anatomy one by one. First, we'll see some craniometric landmarks and also some cortical and subcortical anatomy. So this is an image we're all familiar with. Just to show a very familiar points, this is the pterion. This region is the pre-occipital notch in just at the root of the zygoma. This is the asterion. This is the urion or the parietal tuberosity, which has its own importance. This is the region of the coronal suture. Where the superior temporal line and the coronal suture meet is the stephanion, which is again another important craniometric point, and this is the bregma. So let's start looking at the cortical anatomy. When you open the region of the pterion, what is important is the most important structure inside is when you open the pterion, you reach the anterior Sylvian point. The anterior Sylvian point is this region. It is a region in the Sylvian fissure where the pars triangularis is retracted upwards, and there is a wide cavity there through which you can enter. If you enter, you will straight land into the ansular apex, and it is the most important region to open the Sylvian fissure, dividing the proximal and distal ends of the Sylvian fissure. After you remove the sutures and the bone in that region, this is the structure that you will see. This is the inferior frontal gyrus. This is the precentral gyrus, the central sulcus, and the postcentral gyrus. The important areas in this region are this yellow circle here that consists of the pars triangularis and the pars opercularis is your traditional Broca's area. And this blue circle here, that is this fold that connects the pars opercularis to the precentral gyrus. You can see this characteristic fold. And this region is the ventral premotor area, or when you stimulate this area, this is the area that is important and it will cause speech arrest. So these are two important cortical landmarks in this region. When you look on the superior surface, there are other important landmarks. So this is the central sulcus, this is the precentral gyrus, and the postcentral gyrus. So this knee here of the precentral gyrus, this is a region that is the omega region. It is just posterior to the meeting point of the superior frontal sulcus and the precentral sulcus. So this meeting point here, this middle knee is very characteristic, which has an omega shape, which can also be seen on MRI. And this is the hand motor activation area of the motor cortex. This yellow circle here is the supplementary motor area. What does the supplementary motor area do? It performs learned activities. It is in the posterior part of the superior frontal gyrus, and just anterior to this SMA is the pre-SMA, and it learns sequential. This helps in performing the learned activities. The pre-SMA actually learns the activities. And this region here, this blue circle here, which is the region where the most caudal part of the superior frontal sulcus, where it joins in front of the precentral gyrus, this part of this cortex is the dorsal premotor area, which is also important in performing motor activities. Craniometrically, these landmarks can be identified. If you see this is the region of the bregma, so 1.5 centimeter behind the bregma, 3 centimeter lateral. In this area, you will get the meeting point of the superior frontal gyrus, superior frontal sulcus, and the precentral sulcus. And just posterior to this region is the hand motor activation area. This is the superior Rolandic point as the central sulcus turns into the interhemispheric fissure. That is again important to identify the posterior aspect of the central sulcus and the postcentral gyrus. Medially, both the central and the postcentral gyrus, precentral and the postcentral gyrus, meet below the central sulcus and form the paracentral lobule. They also meet laterally to form the subcentral gyrus, which I will show you in a later image. This is the region of the paracentral lobule. This is the region of the precuneus. So medially, what do these things correspond to? So the coronal suture corresponds to the interventricular foramen of Monro. The paracentral lobule corresponds to the ventricular atrium. The central sulcus, if you look right down, you will see that it corresponds to the pineal region or the quadrigeminal cistern. And this region here, where the superior frontal sulcus and the precentral sulcus meet, which I showed you in the superior surface of the hemisphere, is actually corresponding to the superior surface of the thalamus. So these are important craniometric points that you remember when you're operating on the brain. This is another important cortical landmark. So you see this is the middle frontal gyrus. and it always consistently joins the precentral gyrus in this area here, forming the middle knee of the precentral gyrus. And this region, the caudal part of this region, consists of the frontal eye field, and it is involved in saccadic movements and involuntary eye movements. Again, some important craniometric points. So this is the inferior Rolandic point. This is the point where the precentral and the postcentral gyrus meet below the central sulcus and form the subcentral gyrus. And it is present at the highest point of the squamosal suture. So this is a squamosal suture, the highest point of the squamosal suture, intersecting with this vertical line drawn from the pre-occipital notch. And this is the inferior Rolandic point. This is the other important point that you remember. This is the Stephanion. This is the region where the coronal suture meets the superior temporal line. And inside the brain, the cortical landmark that it corresponds to is the face motor activation area on the precentral gyrus. So these are some important cortical landmarks that we have seen on the frontal aspect of the hemisphere. Now let's go into the subcortical region to see what fibers come in the way. So recently we published this paper. I defined this architecture and function of the brain by classifying the white fibers of the brain into various layers. This table here actually shows which white fiber will come under which gyrus. So each gyrus of the brain was dissected to find out which part of the white fiber will be present beneath that gyrus. So this is the table showing that. And this is the classification of the white fibers. So we divided into 5 layers. So we have 4 horizontal layers. The superficial group is this yellow circle here, or the short association fibers, or the short arcuate fibers. This purple circle here is the middle group that consists of the long association fibers. So like the cingulum, the SLF1, the lateral part of the SLF, or the SLF2 and 3. This red circle here is again association fibers that are in relation to the ventricle. So this is the fornix, the stria terminalis, and all those tracts. The green circle here occupies the center of the system, and that is the commissural fibers. So the corpus callosum, the habenular commissure, the posterior commissure, the anterior commissure, all come in this region. And this red circle is actually the projection fibers. So there is a vertical group of projection fibers that runs in the middle of the hemisphere and divides the hemisphere into a medial and lateral aspect. Fibers which are on the medial aspect of the hemisphere do not cross to the lateral side, and fibers which are on the lateral aspect do not cross to the medial side. The only fiber that crosses it is in the anterior commissure. And I will show you the anatomy of the anterior commissure at the end of the lecture. So let's go back to dissecting beneath each gyrus what fiber system comes. So this is the frontal aspect of the brain. This is the frontal, parietal, and temporal opercula. So now classically you can see the parts of the inferior frontal gyrus. This is the pars orbitalis. This is the pars triangularis. This is the dilated cistern space in the Sylvian fissure, that is the anterior Sylvian point. And this portion is the pars opercularis. This is the part where the pre and the post central gyrus meet as the inferior Rolandic point. This is the subcentral gyrus. So once you remove the gray matter on all the surface of the brain and into the crevices along the sulci and the gyri, you'll start seeing this. You start seeing the U fibers, or the short association fibers, as you can beautifully see here. This is a 7 Tesla image of the brain. And you can see how beautifully the short arcuate fibers are present and how beautifully they connect to each other, and how numerous connections are there between each and every gyra in the brain. So once you remove all the gray matter, this is what you'll see. So you see the connections between the various gyri. You see this connection. This is the middle knee, where the middle frontal gyrus is connecting with the precentral gyrus, and how the middle frontal gyrus connects with the inferior frontal gyrus, and so on and so forth. So these are the short arcuate fibers. In the depth, you have the U fibers connecting the hemispheres. Once I remove the short arcuate fibers from the lateral aspect of the hemisphere, this is what I'll see. So once you remove the middle frontal gyrus and the inferior frontal gyrus and go behind, you'll have the superior longitudinal fasciculus, which is traditionally called into 2 parts, the 2 and 3. But I like to call them as the lateral part of the SLF, as they lie lateral to this projection group of fibers. So this is the SLF. This structure, this fiber here, that is going from this anterior aspect of the inferior frontal gyrus to the temporal lobe, is the arcuate fasciculus. And this is a short arcuate connection between the inferior frontal gyrus and the arcuate fasciculus. Now all the gray matter has been removed here, and you can see more clearly the lateral part of the SLF as it is running from the middle and inferior frontal gyri to the supramarginal gyri and the superior parietal lobule. This is the arcuate fasciculus. Now all the gray matter has been removed and you can see all the fibers quite beautifully. These are fibers of the corona radiata as the external and internal capsule meet above, behind here, and they join above and form the corona radiata. This was from the lateral aspect. When you see from medially, this is the cingulate, this is the cingulum. Once I've removed the cingulate gyrus, and you see how the cingulum connects prominently with this region of the precuneus. It also has a prominent connection in this region, that is the superior frontal gyrus. And the layer above this, these fibers that you see here, are the SLF1 or the medial part of the SLF, as I like to call it. It connects the superior frontal gyrus to the parietal lobe. Why are we studying all this? Now, recently we have come up with this concept that gliomas are basically confined to a named white matter tract. What does it mean? That a glioma arises from a white matter fiber and it displaces the adjacent normal fibers. With this understanding, you can change your concept of surgery of gliomas, which I will show you in the next slides. So this is a recent publication where we have proposed a novel classification of gliomas based on its origin of the white fiber tracts. I will briefly show you. So I've divided it into the localized group and the diffuse group. So the localized group of gliomas arise from the short arcuate fibers or the superficial system. They remain confined to one gyrus, or they connect to the adjacent gyrus by the connection of the short arcuate fasciculus, short arcuate fibers. So if it connects here, it will connect to the middle frontal gyrus. The next type is the diffuse type, and these arise from the long association fibers or the commissural fibers. So you see, this is a cingulum. When a glioma arises in this region, it will spread along the cingulum, along its connection to the precuneus. And I will show you images where you can see this very clearly. And then you have the commissural fibers. Gliomas in this region tend to be bilateral, and they involve various parts of the corpus callosum, which again, I will show you. So based on this understanding, this is a recent concept that has been proposed by Professor Goel, an en-masse tumor surgical resection for low-grade gliomas. And I will show you several videos on this subject, how we are operating on these tumors. So of course, while operating, you have various adjuncts. You have the sonography, you have the neuronavigation, DTI, intraop MRI. These are all adjuncts to your surgery. The basic necessity is anatomy. If you know your anatomy, you will be able to perform a good surgical resection. So for an example, this is a tumor, as you can see here in the left side in the supplementary motor area. This is the central sulcus, this is the precentral and postcentral gyrus, and classically you see this tumor in the supplementary motor region. So this is the region anatomically displayed. Now we have to understand where the fibers are. So this region, the corticospinal tract will be displaced laterally and posteriorly, as you can see in this DTI image. And if you enter, it is surrounded here by short arcuate fibers. So if you can enter here, you can easily perform a safe and mass resection. I will just show you quickly a short video. So earlier in the series, we performed monitoring in all of these patients, but nowadays we don't use intraop monitoring. We just use them for very small, some patients. So this is the you can identify the tumor visually. Once your experience in the field increases, if you reach the anatomical location, you can use sonography and neuronavigation initially, but later on you will start being able to identify the region of the glioma visually. You can make out from its color, you can make out from its consistency. And here you can see that we are separating it from the normal fibers. I will just run this forward a little bit. And you can see that a plane is being developed. This a very definite, well-defined plane can be developed while operating on gliomas if you understand the anatomy of the region and understand where the fibers are displaced. So if you see this gyrus here, this is actually the precentral gyrus, and the tumor is being dissected all around from this region in a definite plane. And if you are able to identify and define this plane, you will be able to perform a good radical resection without causing any post-operative neurodeficit to the patient. I will run this fast, and you can see here that the tumor is being dissected in that plane. The plane is being maintained, and a complete en-masse resection of the glioma is being performed. You can see now the normal structures that are coming in this region. You can see the normal white fiber. So the normal white fiber that will be there in this region is the middle part of the SLF that will come here. And now you can see that the whole tumor is being resected in an en-masse fashion, where the whole tumor is out. And you can see the post-operative image. a supratotal resection of the tumor has been performed. There is no flare signal abnormality. If you see the recordings, the MEPs are completely maintained, and this is the specimen of the tumor, and the patient is doing well without any post-operative deficit. This is another patient that we've just operated 10 days back. Again, another tumor in the supplementary motor region, again operated by an en masse surgical strategy, and you can see the post-operative image. This is an interesting case where you can see that the tumor is just abutting the precentral gyrus. So this is your central sulcus. This is the region of the precentral gyrus. The tumor is almost abutting there. But again, if you understand anatomically that it is confined by the short arcuate fibers, it is confined to that gyrus. The other fibers are displaced there, then you will be able to perform a radical safe resection by identifying and defining a plane of resection in this region. So again, another video. We have identified the glioma visually. Of course, we can use sonography and neuronavigation, but nowadays we are just using them as confirmatory tools because we are able to identify them on anatomical basis and by visual impression. No need of any fluorescence or any such things. You know the anatomy, you know where the tumor is lying, and you go in and remove that tumor. So you can see here that the tumor is being dissected. A well-defined plane is being formed around the tumor. This is again the region of the central precentral gyrus, and you can see how you can actually feel the plane. You can feel how firm the tumor is. It is different from your normal cortex, and you can go about and remove this tumor in an en masse fashion, as you can see here, and you start identifying the normal structures in the depth of the tumor, and the whole tumor is being resected. Another important thing is that there is no need of much coagulation in this region. You can see that there is hardly any coagulation being performed, and the whole tumor is being removed en masse. And this is the post-operative resection cavity. This is the central precentral gyrus, which is beautifully maintained, as you can see here, and this is the tumor resection. This is the post-operative image, and this is the patient. You can see that there is no post-operative deficit. This is a tumor in the inferior frontal gyrus. So you can see by functional MRI, you come to know these are aids. In the beginning of your surgery, you use these because they will aid you, but you cannot depend on them completely because you have to know the anatomy. So you know where the tumor is lying, and you go in and operate on this tumor. This is another tumor that is lying in the region of the middle frontal gyrus. So the tracts that are displaced, corticospinal tracts are displaced posteriorly. You see the lateral, the SLF and the SLF2 and 3 are displaced laterally. The middle part of the SLF is displaced posteriorly. This is downwards. This is the functional area, and this is the post-operative cavity with after an en masse surgical resection. This is a diffuse tumor. You can see here, this is a diffuse tumor. It is involving the superior longitudinal fasciculus, the middle part of the SLF, as you can see very clearly here. And you can perform this en masse resection by identifying the plane. This is the cavity interhemispheric approach, and here you can see the tumor resection. This is again a tumor in the region of the pars orbitalis, where again it is safe to perform an en masse resection because there are not many proper fiber tracts that will be damaged in this region. Again, this is another tumor here that is in the region of the middle frontal gyrus, and you can see a delayed image. There is complete tumor resection, en masse strategy. Patient is doing very well. This is another recent tumor that we have operated last month. This is a tumor exactly in the operculum, in the inferior frontal gyrus, as you can see here. So we've used neuronavigation here, and you can see that the fibers that are displaced, some fibers at the arcuate fasciculus will be displaced medially by the tumor. So if you remain within that plane, you'll be able to properly dissect it. So these are the cortical areas that are important. So this is the Broca's area. This is the area of speech arrest. This is the region of where the tumor is lying. The arcuate fasciculus will come here. The IFOF will not come too much in the way because it is way in the depth in this region. The main one that you have to take care of is the arcuate. And here you can see that an en masse surgical resection will be performed. I will just run this through because of shortage of time. So the tumor is here. You can see, you can make out. See this region here. This is whitish. This is the normal area. So you can actually make out. See this whole plane is the tumor. You can actually make out visually. I'm not sure if you can appreciate, but if once you are inside the operation theater and seeing under the microscope, you can definitely make this distinction and identify a low-grade glioma from the normal cortex. It takes time. It takes experience. But once you start doing it, you will be able to identify it. See, you can see this tumor, and you can see the well-defined plane that is being formed around the tumor. And here you can see again that it is being dissected. So you could identify it from the normal cortex, and the whole tumor is being resected in an en masse fashion without any coagulation. Here you can see that the vessels are also preserved, as I will show you at the end. When the tumor is being separated, all these vessels are preserved, because if you damage this, you are in the speech area. You might cause a deficit. So it is important to preserve all these vessels that are running around the tumor. And this has been eminently done here, as you can see. There's the last bit of the tumor being removed. And that all the vessels are preserved in this region. And this is the post-operative cavity. And this is the patient at the end of surgery. And you can see there is just a very mild discharge. Which so you will not understand the language, but this is on second day of surgery, and you can see that the speech is completely maintained and he's doing quite well. So these are some tumors in this region. Now let's quickly go into the other regions. So this region is your classical Wernicke's area, where the superior temporal gyrus meets the supramarginal gyrus. You can see that the Sylvian fissure is ending in this region here. The superior temporal sulcus is ending here. Another important point that I told you is the urion. This is the parietal tuberosity, the most prominent parietal point here. What does it correspond to? It corresponds to the supramarginal gyrus. What is this area? It is part of the inferior parietal lobule, adjacent to the angular gyrus, which is important for naming and which has a myriad of fiber tracts at its depth, which I will show you in later images. This is another important point, which is the meeting point of the interparietal and the postcentral gyri, which lies about 6 centimeter above the lambda and 5 centimeter lateral to it. So again, these regions are important. So this is a tumor in the superior parietal lobule. So you have to understand that the corticospinal tracts are displaced anteriorly and laterally. So medial to it will be the tumor. As you can see in this image here, these are the corticospinal tracts. This is the tumor. The SLF will be displaced inferiorly, as well as the cingulum. So once you understand this anatomy, you can safely go in and perform a resection, as you can see in this post-operative image. Now, what is important is in the depth of this tumor, there are multitude of tracts. So this is the temporoparieto-occipital junction. And what are the tracts that come here is, this is the IFOF that comes from the inferior frontal and runs to the temporal region. Beneath it, you have fibers of the anterior commissure that run. Beneath it, you have the Mayer's loop or the optic radiations. Beneath it, you have the tapetum. Also superficial to this region, you will have fibers of the middle longitudinal fasciculus. So if you see, all these fibers are involved in speech, they are involved in visuospatial attention, they are involved in vision, and all the damage in this area will cause a very heavy damage, especially in the dominant lobe. So it is important to remember this junction. So this is another tumor in the inferior parietal lobule. You can see that how the fibers are displaced medially. So here the corticospinal tracts, which were earlier displaced laterally, will be displaced medially and anteriorly, and you can go in and safely perform a resection. All the other fibers are displaced medially and they will not come in the picture if you remain within this well-defined plane. And this is the cavity after the tumor resection. This is another tumor that we have recently done. Again, a tumor in the superior parietal lobule. This is the central sulcus, post-central gyrus. It is just abutting the post-central gyrus. And you can see an en masse resection. And this is the tumor cavity. And the patient is doing extremely well. Now going into the region of the insula. So this is the frontal, parietal, and temporal operculum. Operculum means curtained. And when you open them, you see the hidden island of the insula, or the island of Real, which is divided into anterior and posterior gyri, anterior short and posterior long gyri, by this central sulcus, which continues in the same direction as the central sulcus of the hemisphere. I'm not going into details of the gyri because we will not have time, but some important structures, as you can see in this image. See, the anterior most part of the insular gyri correspond to the most anterior part of the ventricle or the caudate head. The posterior part corresponds to the atrium, as you can see here. And this is the beautiful hippocampus as it is running from the temporal horn in the choroidal fissure. And you can see the choroidal fissure as it runs all around the insular region. So once you remove the opercula, these are the gyri of the insula that are surrounded by the limiting sulcus. Once you remove the gyri, you start seeing the extreme capsule. These fibers in between are claustrocortical fibers that connect the insular region to the cortex. Once you remove the extreme capsule, this is the thin gray layer of the claustrum that is just lying beneath it. So this is the extreme, this is the claustrum, and these are fibers of the external capsule. Once you remove that, you start seeing the external capsule in all its glory. Beneath the external capsule is the putamen, and beneath that is the internal capsule. So there are multiple layers before you reach the internal capsule. This is a beautiful image showing the classic spoke and wheel appearance. You can see the gray matter of the putamen, the external capsule, and beneath it in the depth, the internal capsule. This is the IFOF. Now the external capsule is actually made up of two parts. This is the dorsal external capsule and the ventral external capsule. So the dorsal external capsule runs beneath the arcuate, you can see here, joins the internal capsule and forms the corona radiata. And the ventral internal capsule has the IFOF and the uncinate fasciculus. So this is the IFOF running from frontal to temporal to occipital, and this is the uncinate fasciculus. This is the arcuate fasciculus. So this is the IFOF that has been completely dissected out, and these are parts of the external capsule. Now again, this anatomy is important. I will show you how. This is again image we have seen already. This is the temporoparieto-occipital junction. This is the SLF. The arcuate has been cut here. These are fibers of the optic radiation. These are fibers of the IFOF. So once you remove the whole putamen, you start seeing the internal capsule, the anterior limb, the genu, the posterior limb, the sublenticular portion, the retrolenticular portion, and the sublenticular portion, that is the Mayer's loop, and the internal capsule in all its glory. Now this relation here of the temporal horn and the Mayer's loop is another important cortical subcortical landmark that we should understand, because it is important in medial temporal lobe surgery. It is important in epilepsy surgery. So this is a DTI image showing all the fibers in this region. And these are some, I will show you the temporal anatomy after a few images. So these are some perisylvian gliomas which have been resected. By understanding the anatomy of this region without any awake surgery, without any intra-op monitoring, and you can see the beautiful resection that has been performed. Again, this is a region in the tumor in the region of the insula on the left side. You understand the anatomy, you know your limits of resection, and you can perform a good resection. This is a small technical note that I had published long ago of using ICG to identify some vessels during insular tumor surgery. Of course, we don't use this, but that time I found it as an important adjunct to identify this end passage vessel that was going to the central motor area, and it had to be preserved while doing the surgery. As you can see here, this vessel is being preserved, and this is I'm removing the tumor in this region, and the vessel was preserved by identifying it by using ICG. So these are some tumors of the insular region. I will quickly just show you how the fibers are displaced, and you can see the post-operative resection cavity. Now going on the inferior aspect of the brain, we are all familiar with this. This is the uncus, the parahippocampal gyrus, the fusiform gyrus, and the inferior temporal gyrus as it folds over. This is the collateral sulcus. This is the region of the entorhinal area. And this uncal region relates very closely to the cerebral peduncle and the posterior cerebral artery as it runs in this region. These are all important while performing tumors in the middle temporal region and epilepsy surgery. So once you start removing the cortex of the temporal region, this is the optic tract, this is the gray matter of the uncus. You remove the parahippocampus. The first layer that you see here, this layer here, is the radiation of the cingulum. This is where the cingulum ends. Beneath that, you have the ependime of the temporal horn. Once you reflect that, you see the hippocampus beautifully, and in the roof of the temporal horn, you see the amygdala. Once you reflect both of them, you start seeing the Mayer's loop as it originates here in the lateral region of the lateral geniculate body and runs into the roof of the temporal horn and then in the lateral part of the temporal horn. This is the loop that we have to avoid while performing epilepsy surgery, while performing amygdalohippocampectomy. So you can see this loop that is going in the lateral aspect of the temporal horn, which is again identifiable here in this region. This is the region of the Mayer's loop. So now this is important. Why? Because if you see this region, this is a specimen. Now I've turned it. So if you see this region here, this is the IFOF. This is the Mayer's loop as it has turned. So there is this area in the anterior aspect of the temporal horn, which is completely devoid of any white fibers, there is no fiber that will get damaged if you enter the temporal horn in the anterior aspect. So Professor Goel had devised this approach to the middle temporal gyrus. You enter the temporal horn in this region, which does not have any white fibers. You straight enter the region of the hippocampus. And if you understand, this is the head of the hippocampus, body and tail, and you resect this whole area en masse for a temporal lobectomy along with an amygdalohippocampectomy. This is the region of the roof of the temporal horn where the amygdala will come into the picture. So again, another image showing the amygdala, the hippocampus, and this whole region that will be removed while performing an epilepsy surgery. So again, this image shows very clearly how this region does not have any fibers. So this optic radiation Mayer's loop is in the roof here, and then posteriorly it goes in the lateral aspect of the temporal horn. So this place can be safely entered and surgery can be performed. Also, this route can be used to perform tumors of the limbic and paralimbic system or the medial temporal region. So you see this tumor in the middle, in the region of the parahippocampus that I've removed by using this middle temporal gyrus and approach between the middle and the inferior temporal gyrus. And you can see the resection here. There's another huge tumor in the parahippocampal gyrus. So you understand the fibers that are displaced. So when you enter from this, all the fibers are displaced superiorly. So you're entering in this region actually. So you're not going to cause any damage to any fibers, even the optic radiation. And you can see the radical resection that has been performed. Now this area is a relatively safe area in the inferior temporal gyrus. There is no fiber here. The only one that is the ILF that will be pushed superiorly by this tumor, and an en-masse tumor resection can be performed. Now lastly, the occipital lobe. It has not very consistent gyri and sulci, but the main ones are the superior occipital gyrus and the inferior occipital gyrus. The inferior occipital gyrus continues medially as the lingual and laterally as the inferior temporal gyrus. The superior temporal gyrus continues medially as the cuneus. You can see this region quickly. This is the parieto-occipital sulcus. This is the calcarine sulcus. You can see this wedge-shaped region is the cuneus. This is the lingual gyrus. Now the parahippocampal gyrus continues both as the cingulate gyrus and as the lingual gyrus, as you can clearly see in this region. So this image we've already seen. These are some craniometric points. This is the ophistocranion, which is the most highest point on your occipital tuberosity, corresponds to the calcarine sulcus. Now, while performing lesions in this area, you have to remember one thing. The ventricle is your boundary. So the occipital horn of the ventricle is your boundary. Medial to the occipital horn is the fibers of the forceps major. And lateral to the occipital horn are the fibers of the optic radiation. So if your tumor is in this portion, if you enter from this region, you will not cause damage to the optic radiation. And if your tumor is lateral to this, if you enter from laterally, again, the optic radiation will be in the depth and you will not cause damage to it. So this, you can see this tumor in this region, middle occipital region. The optic radiation will be in the depth here, and you can easily go ahead and remove this tumor by an en-masse strategy, as you can see in this post-operative scan. And this is a delayed image showing the tumor resection. This is another small tumor that is actually lying in the region where the cingulate gyrus and the parahippocampal gyrus meet in this region. It is surrounded by the forceps minor, and we have reached this tumor using neuronavigation. You can see the fibers that are displaced in this region, and this is a delayed image showing the interhemispheric approach and beautiful tumor resection. This is the orbital surface of the frontal lobe, which is divided into parts by the cruciform sulcus of Rolando in the anterior, into the anterior, posterior, middle, and large orbital gyri. Why this is important? There are some cortical landmarks here, which are very useful for deep-seated tumor resections. So earlier we had used this publication to approach lesions in the region of the frontal horn. So this approach, orbital cortical approach, was devised by Professor Goel during that time, and we reached lesions in the lateral aspect of the frontal horn. Now recently we have come up with this new publication where we devised two trajectories to reach the caudate head. And it is the shortest and the safest trajectory to reach the caudate head in this region. Otherwise, you have to come interhemispheric or contralateral interhemispheric, which gives a very long route. So these are 2 points. This is the medial cortical trajectory. This is the lateral cortical trajectory. This is to the medial orbital gyrus. This is to the lateral orbital gyrus. And you can see the arrows showing the trajectory to reach the caudate head lying in this region. And this is the inferior aspect to show that there are no fibers that come in this way. So this is the anterior commissure. These are fibers of the uncinate fasciculus, which are way in the depth. They will not be damaged by this approach. This is an upturned image. This is the frontal brain, the temporal brain. And when you enter from this region, you can see that there is no fiber here. This is the region of the forceps minor here. There's some fibers, and this is the region of the IFOF. So either you can approach from here or here without causing any major damage. And you can see this huge tumor in the region of the caudate head, operated by a lateral orbital trajectory. You can see the DTI image showing the displacement of the fibers, and a radical resection of the tumor has been performed. And lastly, my favorite, the limbic lobe and the Pappé circuit. So this is the middle aspect of the hemisphere. So this is the cingulate gyrus. You can see that the cingulate gyrus continues here as the parahippocampal gyrus. So once you start removing the fibers of the gray matter in this region, in the middle aspect, this is the region of the thalamus. You removed the gray matter here. This is the mammillothalamic tract and the mammillary body. This is the region of the corpus callosum, as we know very nicely. So once you remove the cingulate gyrus, this is the cingulum. It originates here in the subcallosal region, runs and posteriorly over the corpus callosum and ends in the parahippocampal region here. You see the connections of the cingulum to the precuneus to the superior frontal gyrus. I've cut the corpus callosum and you can see the caudate head. So this region, you can see the fornix, which is ending in the mammillary body, mammillothalamic tract, anterior nucleus of thalamus. To trace the connections further, I have removed the caudate head, and you start seeing the anterior thalamic radiation as they join the cingulum. And now you can see the whole pappage circuit. This is the hippocampus, the fimbria, the fornix, the columns of the fornix, mammillary body, mammillothalamic tract, anterior nucleus of thalamus, the anterior thalamic radiation, joining the cingulum, and which turns and comes back to end, as I had shown you on the inferior aspect, the radiation of the cingulum. So this is the whole pappage circuit, which was then dissected outside by me and my colleague, Dr. Sukhdeep. These are some other connections of the limbic system. That is the medial and lateral olfactory striae connecting to the limbic system. And this was the paper that we published. And understanding of this has led to understanding in limbic and paralimbic tumor surgery. So the region of the parahippocampal gyrus. Again, the approach that is used is from the inferior aspect on the inferior temporal gyrus, which is safe because all the fibers are displaced superiorly, and you can see the tumor resection. As I had shown you earlier, this is a connection of the cingulum. So this is a diffuse glioma. I showed you in the initial images. So this is a tumor that is arising in the region of the cingulum and following it along its trajectory to the precuneus. You can see it very clearly in this image. The fibers, the vertical group of fibers are displaced laterally by the tumor. Here you can see that this is the red color is the tumor. This is the corticospinal tract. The other tracts are displaced laterally, and you can come interhemispheric and perform a good radical resection. The corpus callosum has tumors. Basically, if they arise from the corpus callosum, they will be bilateral. See this image here? So the corpus callosum has so many radiations, as I will show you now. So this is the forceps minor. This orange one is the forceps minor. This is, I call it the anterior radiation of the corpus callosum. The purple one are the dorsal radiation, the radiation that go up to connect the frontal and parietal gyri. The yellow one is the forceps major, which connects the posterior part of the hemisphere. The pink one is the tapetum. So the tapetum actually comes over the corpus callosum, covers the roof of the atrium and the temporal horn, and covers its lateral aspect. So it actually runs over the whole aspect of the temporal horn and the atrium. And these are some fiber, green color one, are the fiber connection of the corpus callosum to the caudate head. So basically the corpus callosum connects your entire hemisphere by some means or the other. This light blue fiber tract is the IFOF, and you can see how closely related the connections are. So when you're performing a callosotomy, in the anterior aspect, if you are anterior in this region, if you perform a callosotomy, anterior to this connection of the pre and post central gyri, then you are safe. And posteriorly, if you perform a callosotomy in the region of the precuneus, again, you are safe without causing any deficit, you will be able to enter. And while performing disconnection, the whole area has to be disconnected, including this circle here, so that the motor and sensory tracts are disconnected. So this is just to understand the tumor. So if you look at it just like that, without understanding the morphology of this tumor, you will wonder what this is. Why is it so confusing? But if you know how the corpus callosum radiates, you know exactly how this tumor is spreading. And you can see the DTI images showing the fibers around the tumor. And you can go in and perform a beautiful resection without causing any problem to the patient. And the last one is the anterior commissure, just to show you the anatomy, how the anterior commissure runs from the frontal to the temporal. It has a bicycle handle shape. This is its temporal connection. This is its frontal connection, right in front of the third ventricle. And this is how it joins the fibers of the IFOF, just beneath the fibers of the IFOF, to form the lateral aspect of the temporal horn in this region. And basically it hugs the entire temporal horn. So the anterior commissure actually crosses the vertical group from below, goes across and hugs both the temporal horns and encompasses it, as you can see here. So this is half a hemisphere. This is the anterior commissure going and hugging the temporal horn in this region. And this is the last image showing the beautiful anterior commissure and the fibers of the optic radiation and IFOF as they all meet. So this is the end of it. And this is the classification that I had discussed earlier. As you can see from the medial aspect, the lateral aspect, and from the top. So this is the vertical group that divides the hemisphere into medial and lateral parts. And if you understand this, the understanding of your fibers becomes very easy. So thank you very much. And I hope this has helped you.
Thank you, Prof. Adiba, for a very extensive and informative talk. I think our second speaker, Prof. Danilov, need to start his lecture because he has something on after this. So we will take question after his talk. I think I would like to call upon Professor Danilov, who is also a member of ACNS YNS committee, and have a very active participation in many neurosurgical conferences, have I think wrote more than 70 international paper, and he also a scientist. And I think probably he can tell us more about what type of research he is doing now, especially in the field of neurosurgery. Without further ado, I will call upon Professor Danilov to give his talk. Thank you.
Thank you, dear chairman, dear colleagues, Professor Kata. Thank you for the opportunity to have a talk today, for having me today. And I have to be short in very diverse topic that doesn't appeal much to neurosurgeons, but still, in fact, very confusing for doctors. So ladies and gentlemen, I'm talking about artificial intelligence. A formal definition for artificial intelligence may be a mathematical solution which automates intellectual tasks normally performed by humans. At the same time, the term artificial intelligence is used to name a branch of computer science that focuses on creating intelligent machines that act like human beings in some way. In that way, it implies many smart technologies with human-like behavior. The examples of artificial intelligence are well known. They are computer vision, speech and voice recognition, text reading and understanding, and machine translation. What are the goals of using this computer-like behavior in medicine, or human-like behavior which a computer imitates? The most obvious and general purpose is the automation of medical processes. Imagine a computer that can read medical records, judge medical images, and suggest clinical solutions much faster and more confidently than a doctor can do nowadays. That might be in some way helpful. So what are the current use cases of artificial intelligence in neurosurgery nowadays? To answer this question, recently we have conducted a systematic review of the original research articles evaluating artificial intelligence. So the abbreviature AI stands for artificial intelligence, as you know. And additionally, we used a topic modeling to objectify our findings. And topic modeling is literally clustering articles by topic and identifying topic-specific terms. So we included 327 articles from PubMed in a systematic review. On this slide, you see a tremendous increase in the number of publications on AI in neurosurgery in 2018 and 2019, and it still is going on. The majority of studies were conducted in neuro-oncology, functional neurosurgery, vascular, spinal neurosurgery, and traumatic brain injury. What were the main goals of using artificial intelligence in that field? Let's start with neuro-oncology. So the main goals of using AI in neuro-oncology were non-invasive malignancy grading, which is image-based, and the graph that appeared on the right is a set of words specific for the topic. I'm underlining the most important words for each topic. So next comes non-invasive molecular diagnostics, which is also image-based. brain segmentation and volumetric analysis, and prediction of treatment complications and outcomes. So you see that image analysis in neuro-oncology is the most important trend. And in fact, it's probably one of the most important trend, if not the most important, in medicine, in using artificial intelligence in medicine in general. For instance, in a paper by Drew and co-authors, machine learning algorithms were trained to guess IDH1 status in glial tumors based on MRI, based on magnetic resonance imaging. Another example is a work from Burdenko Neurosurgery Center, which that I come from. A computer can learn how to automatically delineate small tumors when planning a radiosurgery. And you see that the auto-segmentation in this example is pretty close to manual segmentation. And that's very important because this is the point where the efficacy of artificial intelligence comes out. By saying this, I mean that a computer can do this delineation, this segmentation, much faster than doctor. So it's very cost effective, and it's very good to save some time for a doctor to do more complicated things. This slide shows another work by our center in cooperation with our partners. It's devoted to segmentation of glioma images and prediction of clinical manifestations, for instance, paresis in patients with gliomas. And the oh, I missed it. Okay. This is a study of automatic acromegaly detection from facial photographs. It's not our study, but it's a very interesting example of non-invasive diagnostics using just facial photos of patients. Let's turn to functional neurosurgery. In functional neurosurgery, epilepsy diagnostics, outcome prediction, automated seizure detection, and Parkinson's disease diagnostics were the main issues in using artificial intelligence. And in this field, EEG, electrocorticography, biosensor, in addition to magnetic resonance imaging, became very important data sources. This is a typical study aimed at detection of seizure onset in each patient using intracranial EEG. Another interesting example is a focal cortical dysplasia detection using MRI and machine learning. And on the right, you see a study, on the right, you see a study with accelerometry-based wearable sensors used to detect tonic-clonic seizures. The majority of artificial intelligence studies in vascular surgery can be grouped by four main subjects. So aneurysm studies, intracranial carotid stenosis, arteriovenous malformations, and intracranial hemorrhage. And there is a variety of topics in vascular neurosurgery. A typical task for machine learning or artificial intelligence in this field is vessel segmentation. However, there are the examples of studies using heterogeneous data, including clinical text, unstructured images, laboratory data, etc., to be used in machine learning. At Burdenko Neurosurgery Center, we are doing a project on automatic intracranial hemorrhage classification, and we were able to reach the accuracy of 80–90%. So the accuracy of detecting various types of intracranial hemorrhages, subtypes that you see on this slide, is about 80–90%, and we hope to get better results. We identified the 5 main tasks for using artificial intelligence in spinal surgery. They are non-invasive ICP estimation, discharge disposition prediction, gait classification, which is very special for spinal neurosurgery, and complications prediction, which is quite obvious. For instance, a big set of clinical features was used to predict post-operative complications in spinal surgery. And of course, image analysis was also utilized, for instance, to detect spinal deformities on images. Finally, the tasks for machine learning in traumatic brain injury were quite traditional. They were mortality prediction, ICP, ABP, CPP, and autoregulation analysis, consciousness impairment, and TBI severity diagnostics, and TBI outcome prediction. So they're quite traditional for typical studies in traumatic brain injury. However, in these cases, artificial intelligence was applied. I represent Burdenko Neurosurgery Center, which is the biggest neurosurgical facility in Russia and is one of the biggest in the world. And you see the amount of data we collect due to our surgical activity on this graph. That is why the application of artificial intelligence is absolutely reasonable at our center. And I would like to say just a few words about our experience. One of the key directions in artificial intelligence is automatic medical text processing. I would state that this question is underestimated. So the studies which utilize medical information from unstructured text, unstructured electronic health records, they are rare, still rare in neurosurgery. So most of the studies are devoted to medical images, to this type of big data. And medical texts are something that we should really focus on because they contain a lot of useful information that we can use as a secondary source. So we proposed an algorithm to extract information from unstructured medical text at our center, which is very important for morphologically rich languages such as Russian language. And we were able to construct such an algorithm which can give an expert an ability and opportunity to extract lots of data from millions of medical records in a reasonable amount of time. We published this algorithm and applied for a national patent. We created some special software to extract information from medical text. And why do we need that kind of technology? As you probably know, machine learning is very popular nowadays, but machine learning is something mathematical which extracts information from prepared data, and prepared data contain some target variable. So the answer in specific questions. So to get the answer, to prepare data for machine learning, an expert needs to handle tons of data. So our algorithm helps the expert to extract information and to prepare some data sets for machine learning. And here is an example of this algorithm. You see the quality of using our method, for instance, for paresis detection in clinical notes, and you see the quality of this algorithm. We saw that using the combination of machine learning and human expertise can augment information extraction from text. You know that many people have this strange fear that artificial intelligence is something really dangerous, that artificial intelligence equals some artificial mind, which is not really true. And the scientific knowledge says that a combination of expertise, a combination of human efforts with machine learning automation have this potential benefit for patients and for doctors. We also made an algorithm for scientific literature classification and tracking specific topics, and received a best paper award at European Conference in Medical Informatics. In general, we are very enthusiastic about artificial intelligence studies at Burdenko Neurosurgery Center, and we believe that this topic has a really good perspective. So in conclusion, the use of artificial intelligence is becoming a good trend in clinical neuroscience, and we should not ignore it. It is a separate niche in neurosurgery as well. However, the study series are not that big in neurosurgery. You know that the term artificial intelligence is somehow associated with big data. So to make artificial intelligence work in a robust manner, confidently, you have to put a lot of data in it. So nowadays, that's a problem. I mean, data preparation is a problem. And the clinical utility of artificial intelligence is still a subject for evaluation. So we have to put some effort to understand what artificial intelligence is in medicine and how it can be helpful for doctors and for patients. The very last slide, this plot is called a word cloud. It's derived from our operative reports lexicon. I'm showing it in conclusion to remind that today, artificial intelligence is nothing else but an analytical tool. And it's much more important what we see behind this technology. And I do believe that neurosurgeons still see the brain. Thank you so much for listening to me.
Thank you very much, Professor Danilov, for very eye-opening talk on artificial intelligence in neurosurgery. Definitely, this is a growing field, and we come to, I think, the right time to help the neurosurgeon to be more assured that what they are dealing with. To start the ball rolling, probably I will ask Professor Danilov a few questions first, while waiting for the question from the others. What, in your opinion, because neurosurgery is a very, we call it a rare disease in general compared to other diseases, and most of them are, even the single disease, have very heterogeneous presentation by clinical and also by imaging. And there's a very different imaging modality, especially in MRI, and also the sensitivity of the MRI. And now we have a 7 Tesla MRI, and definitely you get more data from a different MRI database. So based on your experience and your study, you think that to get a deep learning in providing algorithm for a diagnosis, what are the minimum critical imaging that you need to at least to get certain level of confidence or sensitivity of specificity? And my second question to you, that do you think in the near future there's a need to have a so-called especially in terms of repository, so people, a neurosurgeon from all the world can try to put in their images diagnosis into one data bank so that you have a bigger data to do such analysis. Thank you, Professor.
Thank you. I'm not sure that I understand the second question, but the first one was what the amount of data is feasible and is enough to study artificial intelligence projects. Well, that's quite a tough question, because the very precise but probably useless answer will be the much more data you have, the better. But in fact, there is an engineering rule that if you see a number of predictors in your data set, like features for machine learning, you need at least 10 observations for each feature. That's much more complicated with images, because normally a specialist for machine learning will tell you that you need thousands of examples, not tens, not even hundreds, but thousands. But that doesn't mean that you can't apply machine learning with hundreds, just because deep learning is a special way of handling data and structured data like images. But you can still do some work with common statistics and with more traditional machine learning approaches, which are logistic regression, support vector machines, random forest, 6G boost, and etc. So that depends. And if you don't have enough data, you still have a chance to try your algorithms on the amount of data you have. There are some ways to improve, to augment the lack of your, or to cope with the lack of your data, and to augment your algorithms, such as transfer learning. For instance, you know that in some institution, there are enough data to cope with some artificial intelligence project, and they can build some machine learning and even put it into the open internet space and share it with you. So you get that machine learning algorithm or model, then you, for instance, a deep learning model, then you add a layer and you train it fine-tune it for your own task, even if you don't have enough data for it. So that's one way to do. The other question, which somehow I'm not sure that I've heard it properly, but probably you asked, you'll correct if I'm mistaken, you asked me, is it true that we need to somehow cooperate with neurosurgeons all over the world to bring some large databases for machine learning? Is that true?
Yeah. Whether there's a need for it, to create big data from many countries, especially in the field of neurosurgery.
The answer of a scientist is, of course, yes. We have to put these efforts to merge a lot of databases to create some good databases for a certain task. But the answer of lawyer or medical regulator could be probably not that optimistic, because there are some limitations in data transfer. There are some ambitions of scientific groups. There is a paradigm of sharing that data, and there is another paradigm of keeping data and not share it just to benefit from this contents in artificial intelligence. It depends, but normal trend is to share data and to merge them in a large database. The only problem in that is that data are very specific to the task that they're used for. That means that you may have some data, you may have some images, but their format, their content cannot be applied for a machine learning task right away. So you need to prepare them. And that is the most tough, the most huge activity that people should concentrate on while preparing data. So analyzing data and machine learning is just the top of the hill. And a lot of work that is in the background is preparing data. So answering your question shortly, briefly, yes, it's better to communicate and to join some data, but for a very specific project each time. So we need to understand why we collect this data, and with a full understanding that we need to invest more in preparing data than in machine learning.
Thank you, Professor. Any other question from other panelists? You can ask.
I have a small question for
just unmute yourself, if anyone.
Professor Shi?
Am I audible, Liu?
Yes, Sachin, please proceed.
Yeah, I just had one a very innocent question from the point of young neurosurgeons who just trying to understand more about artificial intelligence and still learning to do neurosurgery. So, Dr. Gleb, so we are right now in the genre or situation where the artificial intelligence is building up. The clinical understanding of the brain is becoming more and more, like Professor Abhida Shah, she's almost identified each and every white matter tracks, and through connectomics, I think more and more tracks are coming. So do you see, from the point of young researcher who's into the artificial intelligence, so do you see in the future, now even we have the robots who are, we're using them for the spine surgery, although not much for the brain surgery. Do you see in the future, if we program the machines with the help of artificial intelligence and with the help of whatever the history and the clinical data we've got from the patient, the machine can independently operate on the patients, or there is still a scope that even it has to be supervised by the neurosurgeons, or through neurosurgeons may have to intervene at times? What is your opinion?
Thank you very much. That's a very provocative question, because nobody knows the answer. But if we can be really optimistic, that's kind of science fiction nowadays, that you can create a robot that will operate on human brain, because neurosurgery is too complicated, and machine learning algorithms that exist nowadays, they're sorry for saying that, they're rather dull. They are numb in some way. They can solve a very, very certain task which they were trained for. So we do not have any model for artificial brain. So artificial intelligence is not an artificial brain. And from the point of scientific development where we are now, we can't see technology that can solve a surgeon, for instance, tomorrow. But that space fly was a fantastic century, but now it came true. So as far as computer technology, the power of calculations will arise and be enriched. We will certainly see a new level of artificial intelligence that might not happen tomorrow, but who knows, maybe in 10 years, maybe in 50 years, but something will happen for sure. And the only thing is that today artificial intelligence is still a tool, and this tool is operated by human. So I would believe that a most sensible, reasonable way of developing that technologies is some automation which separated by humans, still by neurosurgeons. That's my own opinion.
Sure. Thank you very much. You're doing a great job. I've seen many of your papers. You can even involve our panel, our committee members from the YNS group at all, any help or any survey or any project.
Thank you.
One question for Daniel, is it okay for me? Thank you very much for a nice presentation. So I want to ask, so maybe I think you can collaborate with Dr. Abhidashah about the deep location of the glioma treatment by AI, I think, or some trauma, the severe head injury trauma. Maybe the point of the viewpoint of some cognition function, something like that. So can you tell something about that in the future collaboration?
Thank you, Professor Caudate. We are very open for communication and for collaboration. So as soon as we can discuss, we probably can be helpful in different ways. Because at our institution, glioma surgery is one of the main aspects of treatment, and we're really scientific development of that surgery. And we have some project in studying connectome, for instance, connections which are studied electrically, and we have studies. For instance, you can I can share the context of Ghana, who is very active in that field. So of course we are open for discussion.
Abhida, do you have any question to him?
No, but I agree with some of the things that he has said about at least robot, Sachin asked about robotics replacing. Brain is such an organ, maybe to a point, maybe to the craniotomy, maybe the robot can do. But once you're inside, the variables are so different. You don't know how the brain is going to react. I don't think you can pre-program it to that point, to that precision, where it can entirely take over. Maybe to a point, maybe, the laminectomy can be done, the craniotomy can be done. But the tumor per se, unless it's, really, really small or really non-eloquent, I think we'll have to be there, which is a good. Yeah, and Dr. Denlo, I'll be very happy to collaborate with you if there is.
Yeah, I think so. Yes. I can analyze the very dangerous point, even in the brain. It's a deep place, I think. Thank you. It was a wonderful talk. Thank you.
I have two questions for Professor Abhidashah. May I ask?
Yes.
So there are two questions. One is the classification you mentioned for the glioma. It goes from superficial to deep, like Arcuate Fasciculus is superficial one, and the deep one is the deep white tract. But then, how do you see the Glyometrosis Cerebri? Although it is taken out from the recent classification of WHO, it says that it's just a pattern. But then, why does that kind of pattern happens? Because according to you, you said it has to be either superficial or deep. Then why is we've got this tumor which is superficial also, deep also, multi-centering in both the hemisphere? One question. The second question is, some places they will remove the low-grade glioma in total, like what you are doing. Some places they'll remove like internal debulking and in piece. What I find is when we are doing it, I find it very difficult to remove it en bloc, because when you remove it en bloc, the surrounding edematous brain, that is the place where the bleeding happens, then I cauterize, the vessel goes inside, then I end up more dissecting and cauterizing, doing more damage. So how do I do about that? The problem of achieving a hemostasis as the edematous brain.
Okay, to answer your question, what I've said about classification of tumors is they arise from one specific tract. Like it is not a superficial system. It's a short arcuate fibers. Wherever they are, they might be anywhere. Is the first layer. So those one will be localized gliomas. They will involve one whole gyrus or part of a gyrus. If they spread, they will spread to the adjacent gyrus by the short arcuate connection. Okay, so this is one type. The second type is a diffuse glioma because it arises from long association tracts or it arises from commissural fibers. So what happens to those is they grow along the length of the tract. So if your SLF runs from your inferior frontal gyrus to your supramarginal gyrus, that tumor arising from that will run along that tract. As like the cingulum which is coming above the corpus callosum and going to the precuneus, you can see the glioma that is going along that tract. So glyometrosis cerebri, though it is not there in the WHO classification, I have not seen that many images, but whatever I have analyzed, I have realized that it involves one fiber tract beneath the superficial system, and based on those connections, it spreads. So the corpus callosum, as you can see, it connects to your precentral, postcentral gyri. So if you have a glioma that is arising from the middle part of the SLF, it will go above, it will then involve the other next adjacent tract and then spread across to the other side. So that the pathway of a glyometrosis cerebri is through the white fibers only. Only it depends on which fiber tract it is involving. Suppose it is involving the corpus callosum, it will go bilateral in the area where the fibers are running. So that is the way I think glyometrosis cerebri spreads. And your second question is, this plane does not come, even I could not do it earlier. It comes with a lot of experience. Even we have grown up doing debulking of the tumor and then removing it. But once you start realizing it is not just the surgical aspect, it is the anatomical understanding that helps. That yes, your tumor is in this region. This is the fiber that is involved. The other one is displaced this much. This is the depth that it will probably be. It is a three-dimensional understanding that you get once you have done that many anatomical dissections. And that's how, and then once you start, the consistency of the tumor is different. The color of the tumor is different. You will start identifying it as you do it. And then once you start dissecting in that plane, it comes very beautifully. There is a definite plane that comes.
Because of the pandemic, we're not able to conduct more of this white matter dissection course. How do you think in the pandemic situation, I think it's not going to end at least next 6 months. Maybe we can have some online white matter dissection courses. How can we do it, ma'am?
Yeah, we can do it. I guess we can do it. We'll have to just do it from the lab or something, relay it from the lab or something. We had done once in October last year when we had a meeting. We had done that kind of a thing. It's a little difficult to organize, but can be done. It's not that difficult. We can think about it in the future and we can organize it. From my end, there is no problem. We just need a good internet connection.
Thank you. Dr. Ana Silva is there from Brazil. She is one of the WFNS Young Neurosurgeon Committee member. Ana, you want to ask any question? Anybody has any other
Hello,
questions?
Sachin. I'm sorry
Hi,
not
Anna.
able to open the video. I just would like to thank the opportunity and hope to the online section of this section, if it'll happen in the future. We will be much honored to participate and to divulgate on our social media and bring more students and residents to see it. Our difficulties here with the lab that we are now trying to overcome with the online trainings, the virtual trainings. But I would like to congratulate Dr. Shaha on her presentation. It was very, very delightful, and looking forward for more meetings like this. Thank you very much.
Thank you, Anna. Thank you.
Any other question from the panelists or from the delegates? Dr. Liu, if there are no any questions, can we wind up then?
Thank you, Sachin. Thank you, Prof. Adibasha, as usual. Very good presentation, and I think, and also thanks to Prof. Danilov. Hope to hear more update from you in the future webinars, probably after some collaborative work with ACNS. And before we close the session, probably we call upon Professor Yokokato to give a closing remark. Thank you. Prof, you need to unmute.
Anybody from Myanmar, because of the surgery, invited the several YNS from Myanmar for this webinar? Sachin?
I think we had quite a number of people in the middle, but as we started the discussion, many of them have left. Shui is there. Hello, Shui.
Hi.
Hi.
I'm from Myanmar, but recently now I am in Japan. So I cannot say what really happened in Myanmar. But as long as I know, the conditions are really bad, and now our neurosurgical ward closed, and nobody can join the surgeries or anything, and all the operation, nearly all the operation are stopped, and now people are dying, more than 700. So the conditions are really severe. And most of the doctors are arrested, even some doctors are arrested brutally. So it's a very hard conditions to stay in there.
Anyway, do you have any question to both the speakers?
No. Thank you. Or
maybe Avida Shah, maybe you can have some encouragement word to the member YNS.
So basically for neurosurgery, for you to grow in neurosurgery, I think it is very essential. We of course learn the textbooks and everything, but for your surgery, anatomy is basis. That is what I have learned over so many years. I mean, you learn, you see people operate. If you have to understand it yourself, you have to go yourself. Even when you're doing diagnostics, till you train yourself, till you do the suturing yourself on rat femoral vessels, you're not going to do it. Similarly, once you're reading more and doing more in the lab, your understanding increases very significantly. And it is not that difficult. We might not get a whole body, but for us, we need a brain. It is not that difficult to procure a brain. That is what I say. So the advice is remain in the operation theater and do anatomy. These are the two important things for neurosurgery. Thank you.
Daniel, any encouragement for them?
Dear colleagues, I would say something about the research in neurosurgery. Even though it is something scary, I think this is the only way to improve generally, and that is a way that we can keep our mind open to new technology and embrace it. Of course, I wish everyone health and safety.
I think you should continue the study, even the very bad situation. We'll discuss later. Thank you. Thank you very much for everybody. Both of them very good the talk and very informative for all of us, not only for YNS. Thank you so much.
Thank you, Professor.
Thank you.
Thank you, Professor.
Thank you.
Thank you.
Finish?
Bye everyone. Bye, Professor Kato.
Good night. Thank you for Liu and Dr. Sachin. So we look forward to next meeting. Thank you very much.
Yes.
Bye.